Hi, this is Nathan Zeringue, submitting my major assignment A for Dr. Jimmy Lawrence. So we have the problem statement here, where we have a brick with thermal diffusivity here, thickness of 0.5 meters, and then it gives us that the whole brick is at uniform temperature of 300 Kelvin. So we want to find the amount of time that it takes for the middle to get to 425 Kelvin whenever its surface is the left and right surfaces are being heated at 425 and 600 Kelvin. And so we're given this explicit method temperature equation where the temperature of the node at the time that we're looking at is going to be the stability criteria times the temperature of the node in front of plus the node behind at the temperature prior, at the time prior, plus 1 minus 2 times the stability criteria, and that's going to be multiplied by the temperature of the node that we're looking at the time prior. So we know that this stability criteria has to be less than or equal to 1/2, but we're actually given that we just need to set the stability criteria equal to 1/2, and so this whole third term will cancel because we'll have 1 minus 2/2. And then this is going to simplify to the temperature of the node in front of and the node behind at the time prior divided by 2. So just the average of those two temperatures. And so we're asked to find the amount of time that it will take for the middle temperature to reach 425 Kelvin. And then we want to look at the stability criteria for a 2D and 3D system. And so the thought behind this code is that we have two arrays. The first array is going to be the initial, and then the second array is going to be the explicit method where we calculate the new temperature based on the previous temperature. And then that first array is just going to be a copy of the second array. And we're going to loop that however many times until the middle temperature gets to 425. And so we initialize, we set the length of the brick equal to 0.5, the number of dx segments, the number of nodes, this is going to be 99, which is something that I set in order to get an accurate value for the middle temperature without overloading the amount of loops that it will take. And then so we could calculate the width of each dx by the length of the brick divided by the number of segments that we have. And then because this is 99 dx segments, we know that the middle is going to be the 50th node. And so that's 99 plus 1 divided by 2. So that's going to be this middle. So we could also set our thermal diffusivity and our T left and T right of 425 and 600. And then for modeling purposes later on, we have our T cool and T hot of 300 and 600 Kelvin. And so we're given that the stability criteria is equal to 1/2, and so we know our dx, we know our thermal diffusivity, we can find our dt. So that's exactly what this equation does right here. So then what we're going to do is we're going to make this array of each initial temperature for each node as well as the left and for the right. So we're going to start out, so we're going to go left to right. This initial value is going to be the first temperature, which is going to be the leftmost temperature. And then we're going to loop for 99 times. We're going to add a 300 value to this array. So we're going to have the 425 and then 99, 300 indexes. And then finally, we're going to have the rightmost temperature of 600. And then so I'll come back to this later, but this is for modeling purposes, this T beginning. And then this is going to be the second array. So initially, both arrays are going to be equal. They're both going to be that initial of 425 and then 300, 99 times, and then 600. So this while condition is for the array, the middle of the array, the 50th index. While that is less than 425, we're going to be looping this. The moment it's equal to 425, we're going to break it. So what this loop does is it does the explicit method with the assumption that the stability criteria is equal to 1/2. And then each time this is going to loop, we're going to be adding time, and we are going to be adding 1 to this loop counter. And so what we could do with this loop counter is we can create models while the middle temperature has yet to reach 425. And so I chose to do 4 models after the initial, where we have n divided by 4, n divided by 2, 3n divided by 4, and then n. And so instead of doing a whole nother loop for n, we can just use this, what's going to be this t final. So it's going to be after this loops until this middle temperature is 425, we're going to have the t final. And so this is the exact same code, all of this, except instead of having the condition of while the middle is less than 425, we just tell it to loop n divided by 4 times. So that's what this does. The same thing as before, just looping n divided by 4 times. This does the same thing, except looping n divided by 2 times, and then looping 3n divided by 4 times. And then we have our t beginning from earlier, which is the initial, and then our t final, which is after the middle reaches 425. And so for modeling this, I used mesh grid, and we have that for the actual color distribution, we have the lowest being t cool, highest being t hot, which was 300 and 600 from earlier, because that's the lowest temperature that we ever achieve, which is the initial. The hottest that we ever could possibly achieve is 600. And then we do some cleaning up. We want the title to show us the amount of time it's taken, and then the middle temperature. And so we do that for this initial, and then for the 3 timestamps of n divided by 4, n divided by 2, and 3n divided by 4, which I called tfin 1, 2, and 3. Our tfin here is going to be the actual array whenever the middle temperature actually reaches 425. And so I would do the same thing here as well. And then I plotted a time versus temperature plot of each of the middle temperatures of the beginning array, and then the 3 in process arrays, and then the final array. And here you can see I set the title and the X and Y labels. And so here are the actual models that I made. So here we have where the brick is initially all at 300 Kelvin. The left and the right are at 425 and 600. And then you can see the color bar, which tells us what color represents what temperature. And so here are the 3 timestamps, which are the brick heating up in progress. So we have the time equal to 4.3 hours, 8.6 hours, and 12.9 hours. And you can see that after almost 13 hours, we still have yet to reach 400 Kelvin in the middle. And so here you can see this is the final after the middle has reached 425 Kelvin. It took about 17.2 hours. And then this is my graph of the temperature of the middle of the brick versus time. I was expecting this to have more of an exponential growth due to the middle being close to 300 for a long time, for almost a third of its time. It's pretty close to 300. And then as the edges start heating up, and then it gets to the middle, it's going to get hotter and hotter. However, this is only using the 5 timestamps that I did the models at. So if I had more, I might see more of that exponential relationship. So one application that this might have is that, let's say that we have insulating bricks in a furnace, say like a blast furnace, and say that these bricks decay or degrade whenever the middle temperature reaches 425, because you could assume that the middle is going to be the coolest at any time, since the left is going to be 425, the right is going to be 600 Kelvin. So if the middle reaches 425, let's say that it degrades. So we could say that we can run this blast furnace until the bricks run the risk of decaying, which is about 17 hours. So being safe, you might run this blast furnace for a maximum of, say, 16 hours. We were asked also why the stability criteria is less than or equal to 1/2. So here, this is my original Excel that I used, except I changed the stability criteria to 0.6 instead of 0.5. As you can see, the cell that I have marked here is actually lower than the initial temperature. So it actually cooled down while being heated. And hence the explicit method became unstable, which is why the stability criteria is less than or equal to 1/2. We were also asked what the stability criteria might look like for a 2-dimensional and 3-dimensional system. So again, for 1-dimensional system, we know that the stability criteria has to be less than or equal to 1/2, and that is basically the node behind it plus the node in front of it at the previous timestamp divided by 2, so just taking the average. However, we know for a 2-dimensional system, we're not just going to have left and right to worry about. We're going to also have the top and the bottom heating this as well. So taking the average of that, we have the temperature of the left, right, top, and bottom at the previous timestamp divided by 4 in order to take the average. And similarly for a 3-dimensional system, we have to worry about the front and the back as well. So we have the left, right, top, bottom, front, and back divided by 6 to take the average. And so the stability criteria is going to have to be less than or equal to 1/6. For my major assignment part A2, I chose problem 2-62E of edition 2 of the book, where we have steam flowing through a pipe, and it gives us the length, the inner radius and outer radius, and then the thermal conductivity and heat transfer coefficient of the actual pipe. In addition to this, it gives us the average temperature of the steam and the temperature of the outside of the pipe. So I set the length of the pipe, the inner and outer radius, the thermal conductivity, the average temperature of the steam, the heat transfer coefficient, and the temperature of the outside of the pipe. So from our heat conduction equation, we know that there's not going to be any there's not going to be anything more than one-dimensional heat transfer. We know that we're at steady state and there's no heat generation. So this equation simplifies to d over dr of r times dt over dr. That's going to be equal to 0. So we can integrate this once to get dt over dr is going to be equal to C1 divided by r. Integrate again, we get the temperature distribution across the pipe as a function of r is going to be equal to C1 times the ln of the r plus C2. So we could use boundary conditions here where when the radius is going to be equal to r1, we know that negative k times C1 divided by r1 is going to be equal to h times the average temperature of the steam minus C1 times the natural log of r1 plus C2. We also know the temperature of r2, which was given. That's going to be 160, as you can see here. That's also going to be equal to C1 times the natural log of R2 plus C2. So this is just taken from this equation right here. So I could actually initialize my C1 and C2 and then solve for C1 and C2. And we know everything here. We know T2, we know the average temperature of the steam, we know R2 and R1, we know our thermal conductivity, heat transfer coefficient, and then this is going to be R1 in feet. We could use that to calculate C2. And then we could basically just set up an array similar to what we did in part A1. And then we have a for loop here going from R1 to R2 at 0.01 intervals. And we know our C1 and our C2, so we could just use this equation to find the temperature at each radius. So that's what we do. Then we add our final temperature of the outside of the pipe, which is 160, to the very end of that. And then we model it using mesh grid. Because of the temperature distribution, we actually have our lowest temperature being only 159, our highest being 161 for the color bar, so that we can actually see a difference in the pipe at all. And so here you can see the model that I created, where we have our inside of the pipe obviously being the hottest from the steam, the outside being the coolest at about 160, where the inside was about 160.4 or 160.5. We were also asked to solve for the heat conduction through the pipe, Q, which is equal to negative K times A times dt dr. We could solve this for Q is equal to negative K times 2 pi L times C1, which is basically the area, times C1 over R. The R's cancel. And so this heat conduction actually doesn't depend on radius at all. And when solving this, we see that the heat transfer is equal to 1,757.9 BTUs per hour. And then I solved it by hand as well, as you can see here.